Hello everyone. In this example or this video here, it's kind of uh, a special topic or important topic because in of existence and uniqueness of a solution. Why it's important? Because you do want to know if there is actually a solution, right? Then when you find the solution, is it unique? Or there are other solutions. So here we're going to look at kind of a nice theorem. And this is based on the book you see, of course, here in section 1.2. But of course, any differential equations you can relate this to. So we can consider this initial value problem and this function, of course, here, just talk a little bit about it. It must be well defined for x and at the initial condition. So if f and the derivative of f with respect to y are continuous, functions in some rectangle, and I'll explain what the rectangle is, in some rectangle, that contains the point x naught, y naught, then this initial value problem um, has a unique solution. So the solution exists and it is unique in some interval. This detail, if you do a little more advanced calculus, you'll talk more about it. If not, it just means a kind of a neighborhood or near x naught here or x zero, and I'll show you what it means. Where, of course, this here is positive number. This delta here is a positive number. Kind of I'll give you the chart, then it'll be easy to see. And you understand what rectangle is. So if you, what this says here, that if f and the function, the derivative of f with respect to y are continuous, that's the point here, in some rectangle x between a and b, so x here, a, b, and if y, let's say, let's show you again, between c and d, right? So as you see here, what's going to happen? You're going to have a rectangle. And of course, if the function let's say a curve is continuous here. It's y equal f of x. Then this, all it says that it guarantees that there is a unique solution right here. Where this delta is this distance. All right, so 2 points we need to understand here. When an equation satisfies these hypotheses of this theorem, then we are assured that there is a solution for this initial value problem. It exists, and it is a unique solution. So let's give you an example. So let's say you have an initial value problem. Uh, Described this way. And this is the initial, this is first order, so initial condition 1 is okay. So remember from algebra, what does this mean? It means you have this point 1, 6. So does this theorem apply, or let's say imply existence and uniqueness of solution, right? So all we need to do is find out whether the f and its derivative with respect to y are continuous at this point here, 1, 6. So dy dx is x squared minus x y cubed divided by 3 on both sides. And maybe we can also write it this way. So this is the function f. All right, so what is the derivative of this function with respect to y? Well, this goes to 0. And here, negative 3 y squared. And times x, so negative x, like a multiple there, 3y squared. Then, of course, times 1/3, which is this outside. So negative x y squared. So if we examine f, it is f. It's continuous on this point, 1, 6. And if you examine its derivative with respect to y, it's also continuous in 1, 6. So based on the theorem, there is a unique, or let's write it for you to see. So since f of x, y, and are defined continuous in 1, 6, then the theorem implies existence and uniqueness of solution on x is so 1 plus some delta and 1 minus some delta. Let's rewrite. Didn't work. Some interval, that's 1 minus that, don't cross that. All right. Okay, so you may look into some other examples, and if let's say the y is defined continuous, but when you take the derivative, then the y happens at the bottom. Then, for example, it's undefined at 0, and the point, let's say you have 2, 0, and that y cannot be used, then you will then it may not work for that one. But if it doesn't work for one, doesn't mean it doesn't work at all. It just means you could use another initial condition and it will work. So you'll see those examples. Thank you.